Hello, welcome to Econometrics Melody. In this video, we'll discuss about the student's t-distribution or simply the t-distribution. Before that, let us see some of the useful functions. The first one is about the Euler number, e to the power something. E to the power 0 is 1 and e to the power 1 is the Euler number itself. And e to the power minus 12 is this small number nearly 0. Now let us see another useful functions, natural logarithm. The base in the natural logarithm is the Euler number itself. And we can find the natural logarithm of 0, the natural logarithm of 1 is 0, and the natural logarithm of the Euler number is 1. And exponential and natural logarithm are inverse to each other. That's why we get the result is the input itself. Now let us see the example or the relationship between factorial and gamma. Gamma n is equals to n minus 1 factorial. This is what we want to show by the help of this example. Gamma 9 is equals to 8 factorial and gamma 12 is equals to 11 factorial. And we cannot calculate the factorial of decimal number while we can calculate the gamma. Now let us see some of the formulae of t-distribution, and we will calculate the CDF and PDF as well in our example in the next session. So the mean of the t-distribution is 0 for degrees of freedom greater than 1, otherwise it is undefined, and the variance of the t-distribution is equals to degrees of freedom divided by degrees of freedom minus 2 for the degrees of freedom greater than 2. And if the degrees of freedom is greater than 1 and less than equal to 2, its value is infinity, else undefined. We can calculate the PDF of t-distribution by making use of a couple of gamma functions. So gamma degrees of freedom plus 1 divided by 2 divided by gamma degrees of freedom by 2 and the square root of degrees of freedom into pi multiplied by 1 plus x squared divided by degrees of freedom raised to the power minus degrees of freedom plus 1 divided by 2. We will calculate the PDF making use of this formula as well in our next example. And we can calculate the CDF by making use of this formula 1 by 2 plus x gamma degrees of freedom plus 1 divided by 2 and 2f1. This is known as our hypergeometric function. We'll also use this in order to calculate the CDF, and it takes the parameter 1 by 2 and another parameter degrees of freedom plus 1 divided by 2, 3 by 2 minus x squared divided by degrees of freedom, and these four parameters it is explained over here, and whole divided by gamma degrees of freedom by 2 square root of degrees of freedom into pi. Here the hypergeometric function, it has four parameters, and let us say something about it. So hypergeometric function with the parameter a, b, c, z. So its approximation, this formula is actually the approximation when the absolute z is less than 1. We can use it in this formula, and we will use this formula as well to calculate the CDF. We get the gamma function when we integrate from 0 to infinity t to the power z minus 1 e to the power minus t with respect to t. We have already seen our example that gamma z is equals to z minus 1 factorial, and this can be further broken down in age z minus 1 into gamma of z minus 1. Now let us calculate the CDF and PDF of the t-distribution in our next section. Now let us calculate the CDF of the t-distribution. First of all, we are degrees of freedom is 9, and for the value of x or t to be minus 1. So this is the hypergeometric function related with it, and in its generic form we have this formula 0.5, that is 1 by 2 plus minus x gamma, this is our degrees of freedom plus 1 divided by 2, so 9 plus 1 divided by 2 is 5, and this is our hypergeometric function for the given parameter which we have calculated over here. And after a square root of, here it is 9 means our degrees of freedom into pi, and the gamma of half the degrees of freedom. And let us see, and this t, it is the Stata function to calculate the CDF for the given degrees of freedom. What is the probability of getting less than equal to minus 1? It is 17.17%. and tCDF, this is the Econometrics melody written program to depict the CDF for the given degrees of freedom. 9 less than minus 1, it is 17.7%. 9 less than minus 1, it is 17.7%. Somewhere over here. And now let us see another example where our degrees of freedom is 3 and the t score is 1. What is the probability of getting the score less than equal to 1. Again, this is our hypergeometric function for the given parameters, and this one it is our generic function, generic formula, and this one it is our Stata function. When the degrees of freedom is 3, the probability of getting less than or equal to 1, it is 80.4%, 80.4%, and let us see it by the help of graph as well. Less than 1, it is 80.4%, less than 1 somewhere over here. So by the help of this program, we can plot the CDO for any degrees of freedom. Now let us take the degrees of freedom to be 300, and this is the CDF graph. Now let us calculate the PDF of our t distribution. So for the degrees of freedom 3 and our x is 0.4, let us see how do we calculate the PDF or the probability of getting exactly 0.4. It is gamma and degrees of freedom plus 1 divided by 2, and again gamma half the degrees of freedom into square root of 3 here means our degrees of freedom into pi, and into 1 plus it is our x to the power, it is degrees of freedom plus 1 divided by 2, and divided by 3 it is our degrees of freedom raised to the power minus degrees of freedom plus 1 divided by 2, and t then it is our Stata function to calculate the PDF or the probability for getting exactly x for this value and the degrees of freedom. Now let us see both of them should yield the same result. The probability of getting exactly 0.4 is 33.12%, and tPDF it is the program written by Econometrics melody to display the PDF for the given parameters. In the backdrop we have a normal distribution. So x is 0.4 somewhere over here in between 30 to 35%. Let us see what was it. So it was 33%. Now let us repeat the same process when our degrees of freedom is 12 and the probability of getting exactly 2 I scored 2. So both of the formulas should yield the same result. It is 6%. So for 2 it is 6%. When the value of this 2 it is 6% somewhere over here. This is it. Now let's see another example, and we are going to change the degrees of freedom to 0.1, some fractional degrees of freedom. So this is our t distribution, and at the backdrop we have a normal distribution. For the degrees of freedom 0.5 we get this kind of graph, and as the degrees of freedom increases, t distribution should nearly converge with the normal distribution, and this time the degrees of freedom is 30. We see that the normal distribution and the t distribution is nearly converging. Now let us reinforce this concept, and we are going to increase the degrees of freedom and degrees of freedom from 1 to 12, and let us see what do we see. So as the degrees of freedom increases, it should nearly converge with the normal distribution. This is what we want to show. Let us increase the degrees of freedom 27 to 36, and at this point the t distribution should nearly converge with the normal distribution. So we hardly see any changes. It has almost converged with the normal distribution. Now let us see the area graph. It is again the program written by Econometrics melody. This program is going to be useful in order to test the hypothesis. The distribution is symmetric, so our significance level is 5%. So the corresponding score, t score is 3.184 minus 3.184 and plus 3.1824. This scores over here. So we have 2.5% of the area marked by the yellow color in each of the side, and which add up to 5%. So for this score 3.1824, the area on the right side it is 2.5%, and the area on the left side it is 97.5%. So we can manipulate the t score, degrees of freedom, and significance level as well, and get the desired area graph. So when the degrees of freedom is 24 and for the significance level of 5%, its score value or significance score level, the score is 2.0639 plus minus 2.0639 and plus 2.6039, and our calculated score it is 0.2 somewhere over here. The area between it is 15.68%, and the excluded area is 84.32%. So for the two-tailed test we fail to reject the null. It means that the score 0.2 it lies inside this null region. So for the two-tailed test we fail to reject the null either based on the p-value or based on our score, t score. Similarly, the p-value in both the left tail and right tail test, they are greater than our significance level. That is why we fail to reject the null. Now let us see some of the hypothesis testing. So this is our data set that we are going to use. Now let us calculate the t-test for a single sample, one sample t-test. And let us tabulate income across gender, and we see that the average income is 10,418 and the sample standard deviation is 5,407, and we want to test a hypothesis whether the income is average income is 11,000. So we use t-test when we don't have the information about the population standard deviation. Now let us perform the t-test. The standard error is 1180.066, and we can calculate it by dividing the standard deviation by root n. Our sample size is 21 over here, and we see they are same, 1180. Similarly, we can calculate the t-score by dividing the difference of sample mean from the hypothesized mean with the standard error, and we should get the same result. It is minus 0.49 in both the cases. And let us see the p-value for both two tail and left tail and right tail test. So it is 31, 62 and 68. And let us see if we get the same value or not. 31, 62 and 68. So it is 31, 62 and 68. Now let us display the table of the test once again, and by the help of the graph we will perform the hypothesis test again. T is minus 0.49 and 31, 62, 68. So minus 0.49, 31, 62 and 68. So for the two tail test we fail to reject the null. As the p-value is greater than 5% for the two tail test as well as for the single test, right, both for the right tail and left tail test. So in all of the three cases we fail to reject the null, and we conclude that the income is in fact 11,000. Now let us see by changing the confidence level to 99% if our result is going to change. Again, by seeing the graph, we fail to reject the null for two tail test either based on the score or based on the p-value. Similarly, for the single test either for the left tail or for the right tail test, the p-value is greater than the significance level of 1%. That is why we fail to reject the null in all of the three cases, and we conclude that the average income is 11,000. Now let us perform the two sample t-tests using groups, and let us again tabulate gender by summarizing the income. So we get the income, average income across the gender. So in this sample we see that the average income of male is greater than the average income of female, and they have again the standard deviation of the male income is greater than the standard deviation of female income. So in this context, can we say both the male and female they earn equal income, and we want to test it, and let us tabulate it first. And in order to calculate the standard error, we make use of this formula. Square root of this is n1 minus 1 into standard deviation of 1, that is for male, square, plus n2 minus 1 into standard deviation for female, its square, divided by n1 plus n2 minus 2, and multiplied by the square root of 1 by 14. This is the sample size of male, and 1 by 7, it is the sample size of female. And let us see whether we get the same standard error or not, and we get the same value. Similarly, to calculate the t-score, we take the difference of the mean and we divide it by its standard error. So the t-score is 1.38. They are same, and the degrees of freedom is n1 plus n2 minus 2. So it is 21 minus 2 is 19, and this is how we calculate the p-value for different tests. Let us say it is 90%, 90, 18 and 9, 90, 80 and 9, and 90, 18 and 9. So let us display the table of this test once again, and we will perform the hypothesis testing by the help of graph as well. The t-score is 1.38, 90, 18 and 9, 1.38, 90, 18 and 9, 1.38, 90, 18 and 9. So for the two tail test, we failed to reject the null because we have surpassed this threshold of 5%, and we have quite entered in the region of null. That is why we fail to reject the null in the case of two tail test. And for the one tail test as well, the p-value is quite greater than our significance level. That is why we fail to reject the null, and we conclude that the average income of male and female they are We have performed this test assuming that the population variances were equal, but they were unknown. Now let us perform the same test assuming that the population variance is unequal and unknown. So the variances are unequal, and what is the t-score? T-score is 1.65, and let us remember this percentage p-value: 94, 11, and 5. 94, 11, and 5. 18.46, 94, 11, and 5. And again, for the two-tailed test, we failed to reject the null. And for the single test, either left tail test or the right tail test, if the p-value is greater than our significance level, we fail to reject the null, and we conclude that both male and female earn equal average income. We use the option whales in order to treat the unequal variance in the case of unequal variance, and this is the more robust one. And let us see what is the tabulation like. Our t-score is 1.65, and again 94, 11, and 5%. And let us see it by the help of our graph and make an analysis. Again, we fail to reject the null in case of two-tail test, as well as we fail to reject the null either in the left tail test or in the right tail test, because the p-value is quite greater than our significance level. Now let us make changes in our significance level. For the two-tail test, we fail to reject the null, and for the left tail and right tail test also we fail to reject the null because our p-value is quite greater than our significance level. So we conclude that the average income of male and female are equal. Now let us perform two sample t-tests using variables, that is our unpaired test. And first of all, let us carry out whether we want to say that two variables, they are the mean, average mean are equal. Now let us see how do we calculate the standard error in this case. So standard error is equals to square root of the square of standard deviation of first variable divided by its sample size plus the square of the standard deviation of second variable divided by its sample size. And let us see whether the results are same or different. And 1376, they are one and the same. And in order to calculate the t-score, we take the differentiate of the mean and divide by its standard error, 4.26, 4.26. And let us remember their p-value for this different test: 99%, 0%, and 0%. 99%, 0%, and 0%. Now let us tabulate the test once again, and it is unpaired test. That is why we specify this option called unpaired. And let us remember their score as well as the p-values: 4.26, 9900, 4.26, 9900, and here we have 4.26, 9900. By the help of the graph, this point at the extreme plus minus 4.26, they lie quite away from this null region. That is why we reject the null for the two-tail test, and we conclude that they are not equal. And let us see whether the first is greater, first variable has the average greater, or the second variable. So this, for the left tail test, we fail to reject the null because our p-value is quite greater than our significance level. So we conclude that for the right tail test, we reject the null, and we conclude that the income average of the first variable is greater than the average of the second variable. So based on this test, statistically we can conclude that the average of the first variable is greater than the average of the second variable. Again, here we have assumed that the standard deviation of the population is unknown, but they are equal. Now let us assume that the population or the standard deviation of the population are unequal and perform the same test. First of all, let us see its tabulation. Again, the t-score is 4.26, 99%, 0%, and 0%. We don't see any change in our analysis, even we assume that the population standard deviation are unequal. So we reject the null for two-tailed test, either based on the t-score or based on the p-value. Similarly, the left tail test, we fail to reject the null, and we reject the null in case of the right tail test, meaning that while the first has its mean greater than the second. When the population variance are unequal, whales, this option called whales t-test is very powerful, or the robust one. And let us see whether our analysis, whether it resembles or it differs. Again, we draw the similar conclusion for the two-tail test, either based on the p-value or based on the t-score. We reject the null for the two-tail test, and for the left tail test we fail to reject the null, and for the right tail test we reject the null. And let us see whether we have different inferences by changing the significance level to 1%. Again, our conclusion is the same as the previous one. For the left tail test, we fail to reject the null. For the right tail test, we reject the null. And for the two tail test, we reject the null. Now let us perform the paired t-test. First of all, let us generate this variable and tabulate it. And we will use this difference in mean to calculate our t-score and this standard deviation to calculate the standard error. So let us see the tabulated form of the t-test. So the standard deviation of the difference of these two variables, it is given over here, and this divided by the root sample size, it is how we can calculate the standard error, and they have the same value 1539. And to calculate the t-score, we take this difference value and divide it by its standard error. We get the same t-score as well, 3.8, and our degrees of freedom is 20. Now let us remember the p-value for these three tests: 99%, 0, and 0. 99%, 0, 0. And let's see whether we get the same result: 99, 0, and again 0. Let us once again display the table of paired test, and let us remember it. The t-score is 3.81, 99, 0, 0, and by the help of our graph, we should get the same result. It is 3.8, 99, 0, and 0 as well. So for the two tail test, we reject the null, and the null is difference age equals to 0. So we conclude that the difference is not equal to 0. Now let us see whether the difference is less than 0 or difference is greater than 0. So as the p-value of right tail test, it is less than our significance level. So we say that the difference is in fact greater than 0. So the difference is greater than 0 only when the first variable have the higher average than the second. So based on the pair test as well, the average of the first condition is greater than the average of the second condition. Now let us see if there is any change in our interpretation for the significance level 1%. If our significance level is 1%, so for the two tail test, we reject the null, and it is very clear by the help of this graph. For the right tail test, we reject the null, and we conclude that the first one is greater than the second. And for the left tail test, we fail to reject the null because the p-value is quite greater than our significance level. So there is no change in the interpretation, and that is why we conclude the average of this first condition, or the mean of this first condition, is statistically significant and greater than the mean of this second condition. Now let us see how do we carry out our t-test when we have the immediate input. So let us say for the sample of 28, we have the average 300. And the sample standard deviation is 50, and we want to test the hypothesis whether the average is 290. And let us first of all see the tabulation, and we will see its graphical counterpart. The t-score is 1.05, and the p-value for these tests are 85, 29, and 14. 85, 29, and 14. 85, 29, and 14. So it is 85, 29, and 14, and the t-score is 1.05. So as the p-value for all of these three cases, whether two tail test or the single test, left tail test and right tail test, they all are greater than our significance level. So we fail to reject the null, and we conclude that the average is in fact 290. Will our interpretation change if we take our alpha value as 1%? And let us say, as the p-value is greater than our significance level, so we fail to reject the null in either of these three cases. Now let us carry out the t-test using immediate inputs for two samples. The first one, it is the sample size is 24 and its average is 300, and the sample standard deviation is 50. For the second sample, we have the sample size 29 and its average is 300, and its sample standard deviation is 70, and we want to test whether the average they are equal. First of all, let us tabulate it. The t-score is minus 1.75, and its p-values for the respective tests 4, 8, and 95. 4, 8, and 95. Minus 1.75, 4, 8, 95. Minus 1.75, 4, 8, and 95. And our significance level is 5%. So for the two tail test, we fail to reject the null. For the right tail test, we again fail to reject the null. And for the left tail test, we reject the null because the p-value is somewhat less than our significance level. And we conclude that the average of second sample is greater than the average of the first sample. So for the first case, we have assumed that the population variance is unknown, but they are equal. Now, if we assume that the population variances are unequal, so let us see how does the analysis change, or will it not change. We get the same result for two-tailed test, or we fail to reject the null. For right-tailed test, we fail to reject the null, and for left-tailed test, or we reject the null because our p-value is quite less than the significance level, and we conclude that the average of second sample is greater than the average of first sample. Now let us see if our interpretation is going to change if we specify the option called Welch, and this option is used when the population variance is unequal. When we assume that the population variance are unequal, again we fail to reject the null for the two-tailed test, we fail to reject the right-tailed test, and we reject the null hypothesis for the left-tailed test, and we conclude that the average of the second variable is greater than the average of first variable. Let us see what happens if our alpha label, we set our alpha label to 1% from rather than 5%. Again, we fail to reject the null in case of two-tailed test, we fail to reject the null in case of right-tailed test, and we again fail to reject the null in case of left-tailed test as well, because the p-value in all of these cases, they are greater than our significance level. And in this case, we can conclude that both the samples have same average. Now let us see some of the properties and uses of t-distribution, and I have collected it from different sources, so we can calculate the value of t. Actually, t is the ratio of standard normal distribution divided by the chi-square distribution, where v, this represents the chi-square distribution with n degrees of freedom. Similarly, the t-distribution is used to model the case of small samples and when the population variance is unknown. Now let us see some of the uses. First of all, in statistics, in probability distribution for a random variable, that is the ratio of a normally distributed random variable to chi-square distributed variable. For hypothesis testing and estimation, particularly when the sample size is small or the population standard deviation is unknown. So in case of survey data, test the equality of means between groups, and to test whether a sample comes from a population with a specific mean and standard deviation. And in finance, example to construction, in the construction of a value at risk model, it is used in VAR models because t-distribution can account for the skewness and kurtosis of financial returns data, which is often not normal. In the field of engineering, it is used to model the probability of the failure of a component under given load, and it can also be used to estimate the number of cycles to failure at a given stress level. And it is used in the field of signal processing, used to model the signal to noise ratio and to estimate the parameters of the noise in a signal. In biostatistics, to model the data which follows skew distribution, and in the analysis of survival data, which is often not normal. Used in econometrics and the time series analysis to estimate models with autocorrelated errors, to estimate models with heteroscedastic errors, that is, variance of errors not constant across all observations. T-distribution is used due to its versatility and flexibility. It is used in a wide range of fields and applications because of its ability to account for small sample sizes and unknown population standard deviation, and also because of its ability to model skewed and chaotic data. So it is used in various fields. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Mallory.